So we were doing integrals in R2. Okay, again, it's kind of an extension of what you do in single variable calculus, except that you're doing in a two-dimensional region, which means that you have now a double integral instead of just one integral. Okay, so the motivation was done on based on a two-dimensional thin plate whose mass could be found by integrating the area density across both x and y. All right, and in the case of a rectangle, it doesn't really matter which way you do the double integral. You could do x first, then y first, then x. Okay, it all ends up being the same, and there is no need for any special rearrangement of things. But for a non-rectangular region, like this, for example, okay, you should be careful. You could do flipping of the integrals, but it's not a free business. Okay, so that's why we went through the type 1 and type 2 integrals. So type 1, you have x first, then y. Oh, sorry, type 1, you have y first, then x, okay, because you have the limits going from bottom to top first, y first, then x. And type 2, you have x first and then y. And either of these could be done for most of the problems, and it should give you the same answer. So that's what I did here. This kind of a simple example which you could have done even with calc 1, but just to convince you that you get the same answer whichever way you do it. Okay, so if you do y first then x, it's easy going from the lower curve to the upper curve. If you're doing x first and then y, you go from left to right, but then the only extra thing you have to do is that you have to rewrite each of the functions in terms of x, okay, or x in terms of y, right? So the left one is x equal to y, the right one is x equal to square root of y, but at the end of it, the double integral, which tells you the area between the two, okay, it's still equal to 1/6. Okay, so this was what we were trying to get across with both the examples. Okay, we can change the order of integration for a non-rectangular region if you do it carefully. Okay, and then we did a question on the worksheet, which was here. Okay, which was just to show you that sometimes doing one of them might be easier. Okay, not in terms of being correct. So for example, if you have this triangular region, going from left to right only takes one double integral, while going from top to bottom or bottom to top goes, it takes two double integrals because of the way the triangle is based. Okay, so the purple line has its set of double integral, and the black line here, this one here, or maybe I can use a different color. Okay, the blue line, this has a different set of double integrals. So based on this intersection point here, you have to write it as two double integrals, which it's doable, but it takes double the work, right? So when I say more work than doing dx dy, instead of doing just one double integral up here, you're doing two of them down here. Okay, and I think the one thing that we did not do during the lecture was to actually calculate it, which is just an iterative process. So I've done that down here. Okay, so try to just do that as a good practice. It's a bit lengthy, I understand, because the limits are a bit bulky and the function itself is not the easiest one in terms of the, it's not difficult to integrate, but there are too many terms. Okay, but I've done that here, and I hope all the algebra plays out nicely. Okay, and at the end you get the answer equal to 0. So that's something you should definitely practice to get used to the integration, especially with the iterative process. Okay, I wouldn't recommend that you do this. For example, this is just too much work to do two double integrals for the same problem. Okay, so that's where we stopped. Do you have any questions before we move on? All right, so just to start off today's, since I know the test and the long weekend may have affected some of the things that you learned before it. Okay, so just as a kind of a warm-up example. Okay, this is not in your worksheet, so you might have to just do this without the worksheet. So just let's consider this what a horrible straight line. That's worse, but okay. Let's consider this triangle here with vertices at 0, 1, 0, 3, and 2, 2. Okay, think that's not a bad triangle. So this is the region R. So set up the double integral of f of x, y, whatever that function is. Okay, we don't care, because the emphasis here is on setting up the integral, because integration is something you can do, right? All of you have taken Calc 1 and you have seen the integrations are not anything fancy. So as long as you can understand the picture and set it up, you're almost there. Okay, so set up the double integral of R or over R f of x, y, dA in two ways. Okay, one with dx dy, and the second one with dy dx. And do not evaluate it. First of all, I have not given you the function, so we don't care. Okay. All right. So can you just try that? Take a couple of minutes and see if you understand the meanings of dx dy, dy dx, which you might have to redraw this picture a couple of times to try out the different orientations of arrows. Okay, that's the whole concept of this chapter. Which way do you integrate first and second? Okay, so can you just take a couple of minutes and try that? At this point, all of you should know that when you write dx dy, it's x first, then y, okay? And x first means that your arrows are going from left to right, okay? So you can see it's kind of a slightly opposite problem compared to the example that I showed you from worksheet 8, right? There the triangle was oriented in a different way. Here it's kind of rotated so that it's based on the y-axis, okay? So can somebody tell me, if you're doing x first, will you have one double integral or two double integrals?
Would it be two?
Two, right? Because since you're going from left to right, okay, there are two lines here, okay? So up to here, that'll be one set of double integrals, okay? And so that is going from y equal to 1 to y equal to 2. Your x is going from this line, which is x equal to 0, the y-axis, to whatever this line is, which we'll figure out, okay? And then once you cross this point y equal to 2, and as you go towards y equal to 3, you have a different set of lines, which goes like this. Okay, so this green dashed line is the kind of the boundary where one is kind of transitioning into the other. Okay. Do all of you get that concept? Once you get that, it's easy to write this. Okay, so we need to find the equation of these two straight lines. So this one here has got slope m equal to what is it? To 1/2. So y equal to 1/2 x plus b, and then you plug in one of the points. So when x equal to 0, y equal to 1. So 1 equal to 0 plus b. Okay. So that means the equation would be y equal to 1/2 plus 1, 1/2 x plus 1. Okay, and since we are doing this in terms of x, you have to make a slight adjustment. That would be y minus 1 equal to 1/2 x, or 2 times y minus 1 equal to x. Right? Subtract 1, multiply 2. And similarly, up here, the slope would be difference in y would be, whichever way you look at it, it's going to be negative 1/2, I think, right? So the equation would be y equal to negative 1/2 x plus b, and it passes through the point 0, 3. So when x equal to 0, y equal to 3, so that's going to be negative 1/2 x plus 3. Right? And I hope it satisfies the point 2, 2 as well. When you plug in x equal to 2, you get 3 minus 1 equal to 2. Okay? So from this equation, you get x equal to 2 times y. Was about to write 2 times y minus 3, but it's not exactly true because of the negative slope. So it's going to be 2 times 3 minus y. So the purple lines are going from the same left boundary, which is x equal to 0. Okay, whether it's the lower part or the upper part, it's still x equal to 0, but the right side is 2 times 3 minus y. Okay, so since I have to scroll down, I hope you have the picture in mind. So there are two double integrals here. Okay, the breaking is happening at y equal to 2. Okay, so first it goes from 1 to 2, and then it goes from 2 to 3. Okay, so in terms of dx dy, it's going to be, remember that you have to write the variable first. Okay, no exceptions. So f of x, y, whatever that is. Okay, x goes from 0 to 2 times y minus 1. And those orange lines goes from y equal to 1 to y equal to 2. That's why these pictures are useful. Without that, you will be kind of disoriented. Okay. Plus the double integral from the next set goes from 2 to 3, and your purple lines go from x equal to 0 to x equal to 2 times 3 minus y. And the y coordinates go from 2 to 3. All right. So that is the setup if you are to do it x first and then y. Okay. Any questions on that? Now let's do y first and then x. I'm going to copy that picture here as in redraw that picture here. Okay. So this is 0, 0, 1, 0, 3, and 2, 2. Okay. Now I want to do this, which I'm sure if you understand what we are doing, you will appreciate that this is going to be easier in terms of the amount of computations you have to do. Okay. So the arrows are going from bottom to top, and we already have these equations. This is y equal to 1/2 x plus 1. Okay. And this was y equal to negative 1/2 x plus 3. Okay, so you already have those. You don't have to redo that over and over. Okay, and your x coordinates are going from x equal to 0 to x equal to 2. Okay, so just one sweep of the triangle would take care of the entire region. Okay, so this is a region R. Right. So the same double integral, if you were to do y first, then x would be 1/2 x plus 1 to negative 1/2 x plus 3. Okay, as x goes from 0 to 2, f of xy dy dx. Okay. Any questions? So it's the same double integral, same region, same function, but depending on how you want to do it, it looks different because of the geometry of the region. Okay. So this is one of the things I expect you to know for this week's quiz. You should be able to look at the simple region in R2 and should be able to flip-flop things. Okay. Any questions on this example? Okay, my next question is to compute this integral here. You can pick whichever is easier for you. If you want to do two of them, it's your choice, but I would stick to the one with one of them. Okay, so compute the above with f of xy equal to 1. Okay, this is the number 1. And what does this mean? For the region R. Okay. So let's see. So it's going to be, assuming that I got my equations correct. Okay. Of 1 dy dx remember the iterative process, you do the inside one first. Okay, so you could do this kind of as a separate one, or you could do it right there. It's up to you. The integral of 1 dy would be just y from 1/2 x plus 1 to negative 1/2 x plus 3. And then that's going to be equal to negative 1/2 x plus 3 minus 1/2 x plus 1. Lower upper limit minus lower limit. This is going to be negative 1/2 minus 1/2. That's going to be 1. So it's going to be negative x. And then you have 3 minus 1, which is 2. Okay, so these are kind of easy places to make mistakes. If I'm missing a sign or something, let me know. Okay, and the outer one is, I should be writing inner and outer, not inside and outer, but it's okay. 0 to 2 of 2 minus x dx. Okay, just going to be 2x minus x squared over 2 from 0 to 2. And that's going to be equal to 4 minus 2, which is 2. So for this region R, which was actually this triangle that I drew up here, okay, what is the meaning of this integral? When you write f of xy equal to 1, what exactly are we doing in the context of this triangle?
Are you saying that the area equals to 1 of the triangle?
Area equals to 2, right?
Oh yeah, area equals to 2.
Yeah. So this is the area of the triangle which was given by R. Okay, is that true? Let's see. The base of this base is, in this case, this line here. Okay, so that is equal to 2, and the height, which is this part here, okay, is also equal to 2 because it's going from. So if you place it kind of in the other orientation, the height of this triangle is 2 as well. and the area is half times base times height, which is 2. So nothing surprising there. Okay, it's a double integral of 1 dA. Okay, with the proper limits will give you exactly the same as the area of the triangle. Okay. Any questions?
Sorry, how come you said f of xy equal to 1 in the double integral, just like initially?
How did I do that?
Oh, why?
Oh, I just gave you a problem. So, as an example, right? You can set f of xy to be anything, but depending on what you set your f of xy to be, the meaning of this double integral keeps changing. So I should have written this as an example. So if this f of xy was a function, that will be actually the mass of this triangle, okay, this triangular plate. And if you set f of xy equal to 1, it's going to give you the area of the triangular region. So this is something that I set up, right? Because f of xy is anything at this point. And the meaning of f of xy will give you a meaning for the double integral. Does that answer your question?
Yes, thank you.
Any other questions? All right, so let's do another example to kind of motivate you, okay? Some very special kinds of problems. So next. Compute the double integral. So x goes from y to 1, y goes from 0 to 1, e to the power of negative x square dx dy, okay? Also sketch the region of integration, okay? Not the function, the region of integration, which is the region that explains the limits of the double integral, okay? So sketch the region of integration. Please don't sketch this function. I don't care what that function, well, it is a nice function. It's actually the Gaussian curve, okay? That's the function, but that's not the point here. Trying to ask you to sketch the region, which is that one, okay? So please do only what is required, because sometimes students, they take the graphic calculator and go crazy with these kinds of things. So understand the question, okay? So first you sketch the region and then compute, or compute and then sketch. That's up to you, okay? So can you try that? And tell me what exactly you encounter in terms of the difficulty in this problem, okay? Sketching the region is easy here, okay? It goes from x equal to y to x equal to 1, okay? These are very easy things to sketch. X equal to y is a straight line. X equal to 1 is going to be some straight line that is a vertical line here, okay? You could use a graphing calculator if you really want, but we don't have to. So the coordinates of this point would be 1, 1, because it's x equal to 1 and x equal to y. So that's going to be 1, 1, okay? Coordinates here are 0, 0. And the coordinates down here, the foot of this straight line would be 1, 0, okay? So that is the region of integration. So I'm not asking you to sketch the function, just this triangle, and this is what we have, okay? Not the region above the straight line, it's below it, because you know that your y goes from 0 to 1, okay? So it has to be below the line x equal to y, not above it, okay? And x goes from x equal to 0 to x equal to 1. Okay, so this is the region, okay? So if you were to do this double integral, just like what you were doing so far, you do the inner integral first, okay? And you have integral from y to 1 of e to the power of negative x square dx. Now, who can tell me how to find the integral of this function? So since most of you probably don't know each other and nobody knows who you are, so it's it's one of those times when you can easily speak up without being concerned about your reputation, right? How do you find the integral of this function?
By parts, maybe.
My parts. I like the way you ended it, maybe, right? Any other answers? By parts may not work, but okay, that's a decent answer. Any other answers? I mean, the only techniques are integration by substitution and part. I mean, there are other techniques like trig substitution and so on, but this is probably not a candidate for that, right? The question is, can you find a function, okay, some elementary function whose derivative is equal to e to the power of negative x square? That's what this is about, right? When you find the antiderivative, what you're asking is there a function whose derivative is equal to e to the power of negative x square, which is a beautiful function. It's actually the Gaussian curve, okay, the bell-shaped curve. The answer is, surprisingly, there is no such function, okay? So the maybe is justified, okay, that there is absolutely no technique of integration, or there is absolutely no function that will give you e to the power of negative x square when you take its derivative, which means that you cannot compute this, okay? Then what are we doing here? When I say I cannot compute this, it doesn't matter what levels of math you take, or can keep on learning more math, you just cannot do this integral, okay? If you give it to Wolfram, it'll do some crazy stuff. That's because there are some specialized functions. So those specialized functions are not what we're doing here. We are dealing with elementary functions, which means the functions you have learned so far, okay? This cannot be done. So the technique here, or the trick here, is to reverse the order of integration, okay? So this is a very unique class of problems, which if you set it up correctly, it will work exactly the way you want it, okay? So if you change some of these numbers up here, it's going to fail. So this has to be precisely kind of constructed so that when you reverse the order, it comes out to be in a nice way and you can do it, okay? So reverse the order of integration. What does that mean? You will do y first and then x. Okay, and let's see how that is going to be useful. Okay, instead of doing x first and then y, you're going to do y first then x. Okay, remember, you cannot change this picture. Okay, the picture is the same. The only thing you need to do is kind of, instead of doing x first then y, so this is what initially we are doing. When you say x first then y, this is what we are doing. Okay, because you're going from x equal to y to x equal to 1. Okay, same triangle, we need to go from bottom to top. Okay, so I'm going to redraw that picture here. Same triangle. Okay, this was what we had as x equal to y, x equal to 1, y equal to 0, and this point is 1 1, which means you're going to y equal to 1. Okay, remember that y equal to something is a straight line parallel to the x-axis, x equal to something is a straight line parallel to the y-axis. Okay, basic geometric facts. And this is a triangle. Please don't go into the triangle above it. Okay, that's going to be a failure. Okay, so this is the same region. Instead of going from left to right, now you want to go from the base to the top. Okay, that's what I mean by saying switching the order of integration. What does this mean? Now, x equal to y means, well, y equal to x. Okay. So your y goes from 0 to x. And those red arrows are going from x equal to 0 to x equal to 1. All right. So the switching the order or the reversing the order of integration is not a free thing. So this is not a rectangular region, it's a triangular region. Okay. So you could do it, but do it carefully. So you cannot just say, oh, I'll just put the second one first. No, you take the same integral and then look at the region and see how you can switch them without violating anything else. Okay. So now this is going to become y first, then x, e to the power of negative x square dy dx. Now let's do the inner one first. Okay. Maybe we did something which was going to circumvent your difficulty with this impossible integral, right? So you're doing 0 to x, e to the power of negative x square dy. Remember that you're doing with respect to y, this is a constant. Okay. So for the time being, we can keep that outside. Okay, this is why we are switching the order, because we can take that trouble guy outside of the integral, keep it there for the time being and see what we could do. Okay, integral of dy is y, so it's e to the power of negative x squared times y from 0 to x, which is going to be x e to the power of negative x squared. Now we have some hope because we have an extra term sitting in front. Okay, that gives us some hope. If you have done some integration in your calculus 1 and if you remember it, okay, you probably know what I'm talking about. So now the outer integral, 0 to 1, x e to the power of negative x squared dx. Can you tell me how to do this integral now?
Could you use u substitution?
Yes, and that is probably the only way to do it. So you need to put u equal to negative x squared. Okay, that is the one technique that I want you to know for the semester. Integration by parts, maybe not. Okay, substitution, yes. So u equal to negative x squared, du equal to negative 2x dx. Okay. Now I don't know how you were taught this. You know, I've seen different students do different things. Okay, I think one popular way of doing it is this dx equal to du over negative 2x. Okay, it's probably not a very elegant way of doing it because this term has no meaning as such, but it works. Okay, so mathematically that term has absolutely no meaning, du over 2x. Okay, but for this purpose, it kind of, or for this problem, it kind of serves the purpose. Okay. So you plug in your dx in terms of du, and you can cancel the x and the x, right? That's what you're trying to do here. You're going from the x world to the u world, so it's going to be negative 1/2. But you don't have to write all these details. If you're comfortable using this, just do it. Okay? And that's equal to negative 1/2 e to the power of u, and u is back to our original variable negative x squared from 0 to 1. And that's equal to negative 1/2 times e to the power of negative 1 minus e to the 0, which is 1. Okay. If you like writing this as a positive answer, that's going to be 1/2 times 1 minus 1 over e. And I think on the test, I saw that some of you are passionate about writing answers in decimals. I really don't prefer doing that. Okay. If your answer is in terms of e, pi, and so on, just leave the answer in terms. Those are nice numbers, just or nice notations to leave your final answer in. Okay, so just leave it as 1/2 times 1 minus 1 over e instead of some hideous decimals. Okay. Okay, so this is a very, very important class of problems in section 3.2. Okay, problems where you cannot do the original integral, but you have to do this reversing the order so that the impossibility can be kind of kept outside for the time being, and then you could do it. Okay, very important. So this is one of the items I want you to learn for quiz 3 and also for test 2. Okay? And these problems are kind of very specially constructed. If you make even a small change to this problem here or there, it's not going to work. So if I don't create these problems carefully, it's impossible to solve this problem. Okay. Any questions on this conceptually? So before we start doing the worksheet problems, here are some other functions which you should know have no antiderivatives. Okay. And some of these look very harmless. Okay. So sine of x square, cosine of x square, the square root of sine x, square root of cosine x, square root of tangent x has. If you spend some time, it's doable, but not these two. Okay? That's how bizarre the world of integration is. Some of these cannot be found, some of these can be done easily. Square root of 1 plus x to the 3, okay? Or any small variations of these problems. E to the power of 1 over x. Okay. So these are some of the functions with no antiderivatives, and if this ever appears in a double integral, okay, the idea is that you should be able to do the reversing the order and then do it. Okay. So sometimes the question will say that do this by reversing the order of integration, but if you see these bad functions, okay, be ready to reverse the order. Okay. All right, so let's do a couple of examples in the worksheet. Okay, just to give you some practice. So going to worksheet 8. So I said there is this.
Professor, can I have a question?
Sure.
Can you go back to the problem? Yeah. So like we already have the region of integration. We also have the function of e to the power of minus x squared.
Mm-hmm.
Like how does the whole thing look like in like 3D graphical view?
This is not a 3D graphic. This is a 2D function. So this is the e to the power of negative x squared is a function like this. Okay. That's what e to the power of negative x squared looks like. This, yeah. And then you're going from the original function was x equal to, so you're taking this line and y goes from 0 to 1. So you're trying to compute the double integral, which is under this region here. So this is x equal to y. And this is x equal to 1. Okay. So this point here would be 1, 1. And y goes from 0 to 1, which means this point would be 0, 0. So you're actually finding the double integral over this region here, but which is you're integrating this function in this region. Okay. If you're integrating 1 in this region, it will give you the area of the triangle. You're integrating this, which means that if you consider this as some kind of a plate with exponentially decaying density, then this gives you the mass of that plate between those two limits. Okay, so there are two things here, the function and the region. So, okay. Any other questions?
So if we have like, sorry. So if we have like a z direction, there will be like 3 integration sign. Right?
Yes, yeah. That's a different beast altogether. We are going to reach that maybe later today or maybe tomorrow. Okay. Yes, if there is a third dimension, we need a different integral. So right now we are in R2.
Okay, thank you, Professor.
Yeah. Any other questions? All right, let's do this worksheet, which again, we did this problem in the third week module, so I'm not going to redo this problem again. Okay, so please see the solution from last week. Okay, here is the first one for today. Okay. I always say sketch the region of integration, because without this, you cannot do these problems. Okay. You could sit there and kind of draw it in air and try to visualize that. You don't have to go through all that, funny thing. So just draw something. It's a 2D thing, right? You don't have to draw any 3D pictures. So sketch the region of integration, which I'm insisting that you should do in this question. Okay. And then find this double integral. Okay. So I'm going to help you sketch the region, and then you could do the rest. Okay. So according to this, you're doing x first and then y. You're going from x equal to square root of y to x equal to 1. Okay. You should have some awareness of what these things mean in R2. X equal to square root of y. You're thinking, I don't know what a square root looks like. You could do just square both sides. You probably know this guy, right? Y equal to x squared. It's probably the first non-linear function you've ever seen in your life. Y equal to x squared. It's a parabola, right? So you're going from, so x equal to square root of y, it's just the positive part of the parabola, okay? So like this. This is x equal to square root of y. There is an x equal to negative square root of y on the left side. We don't care about that because we are living in the first quadrant here, okay? X equal to 1, and this is where you have to pay attention, okay? This is where x equal to 1 is, not here, right? That's a big mistake in this problem, because you will keep doing integrals which you cannot do and then start inventing things that nobody else would know, okay? So this is x equal to 1. Okay, so instead of writing this here, let me write it here. X equal to 1 is a straight line parallel to the y-axis. If there are mistakes that students make in this type of problem, they draw the wrong line and then they get into all kinds of trouble, okay? So it's kind of a curved triangle, right? That upper boundary is kind of a parabolic curve instead of a straight line. That's okay. And right now, you're doing x first, then y, because that's how it is given here, okay? So the current state of things, this is how it goes. Okay, x equal to square root of y to x equal to 1. And then you're going from y equal to 0 to y equal to 1. Sorry. Okay, everything makes sense, right? The picture should agree with your limits, and that's what is given in the question. And we want the same picture. Please don't change the picture, okay? Same picture, but the arrows should go from the base to the top, okay? And these coordinates are still the same, 0, 0 to 1, 0 to 1, 1, okay? That's a 1 there, not a 0. And once again, if you are trying to compute this integral and trying to impress yourself or somebody else, it's not going to work, okay? So this cannot be done. So the only alternative here is reversing the order of integration, okay? Instead of doing x first, can you do y first and then x? Okay, now that you have the picture, can you tell me the limits for y and the limits for x? What will be the lower limit for y for these orange lines going from bottom to top, okay? What will be the y for this line here?
Would it be y equals 0?
Y equals 0, that's x-axis, okay? There's nothing fancy about it, that's good. What about that curve that you see up there? How do you write that y?
Would you do y equals x squared? Oh,
yep,
sorry.
I have it right here. No, yep, that's okay. Y equal to x squared, that's, there's not a lot of things you could do here, okay? You have x equal to square root of y equal to x squared, okay? Is there a third thing that you could do? No, right? So you have your y going from 0 to x squared, and your x goes from 0 to 1. Okay. So now the double integral becomes 0 to x squared, 0 to 1, and you have this function 2 plus x to the power of 3 dy dx. Okay, that's why we are doing this. It's not dx dy anymore. Okay, so let's do the inner integral first. We need a bit of room. Inner integral first, and I think I can write this without further explanation, hopefully. Okay, I'm doing y first, so the other function is a constant. Okay, and remember how this function is nicely set up. Okay, you have an x to the 3 here, and we hope an x square comes and saves us by letting us do integration by substitution, and that's exactly what is going on here. Okay, this is x square square root of 2 plus x to the power of 3. And now back to calculus 1. Okay, outer 0 to 1 x square square root of 2 plus x to the 3 dx. Okay, I hope all of you know this. So you can set u equal to 2 plus x to the 3. So du is 3x squared dx. Okay, once again, if you like doing it this way, it's up to you. Okay, so that's going to be the integral of x squared times the square root of u times du over 3x squared. Okay, and that's going to be 1/3. Integral of u to the 1/2 is u to the 3/2 over 3/2. That's going to be 2/3. U is 2 plus x to the 3 to the power of 3/2. Okay, I've seen a lot of students when they do this, they forget writing that exponent of 3/2 when they write their final answer. Okay, I know there are a lot of things going on here, but try to just keep your focus there and write everything. And your x goes from 0 to 1. So that's equal to 2 over 9 times so when you plug in x equal to 1, you get 4 to the power, sorry, what did we say? 3 to the power of 3/2 minus x equal to 0 would be 2 to the power of 3/2. Okay. Again, just put those calculators away, write your answer like this, and just stop. Okay. You don't have to write 1.3224. There is absolutely no need to bring in decimal answers into those kinds of questions. Just write your answer like this. Okay. I'm saying that because in that Lagrange multiplier problem, I had coordinates like 6 over 7, and it looks fine. Why do you want to write it as 0.84? And no need. It's not calling anybody out by name here, but in future try to avoid decimal answers. Okay? Just use calculator only when it's required. We are past that stage where numbers are really the most important part of these problems. Okay, it's more about the concept and what exactly these problems are doing with the pictures. That's what matters. Okay. Any other any questions on this? Not any questions on this example here? Okay, can you try the last one yourself then? Number 3. And it's the last one. It's the last of this type. Okay. Then it gets a little repetitive after a while. The first time you see it, oh wow, this is something very special. But see, do 2 or 3 of them, and you know what to expect each time. Okay, so try this. Okay, so here is the sketch of my region. Okay, y equal to x to y equal to 1. Be careful, it's y first. Y equal to x is this line. Y equal to 1 is this line, not a vertical line. Okay, this is y equal to 1. This is y equal to x. And the problem as given is actually giving you arrows that go like this. Okay, and this goes from x equal to 0 to x equal to 1, which agrees with what we have in the picture. Okay, the picture is always kind of a double, triple check of all your computations and limits. Okay, so now again, this integral here, e to the power of x over y dy, not the easiest integral to do, or it's almost impossible to do. Okay, so we want to shift this so that we could draw the arrows from left to right. Okay, so we could draw this. So the left side is the y-axis, which is x equal to 0. Okay, I'm not really, there's nothing fancy about this region. It's just a bunch of straight lines. Okay, so as long as you don't do anything too silly, it should be easy to do this. Y equal to x becomes x equal to y. Okay, there's no need to take square root or anything. And your y coordinates are going from y equal to 0 to y equal to 1. Okay, make sure that the arrows are sweeping all the way through in the region. Okay, whether it's the orange one or the purple one. Okay, as you go from the extreme values of coordinates, in this case, the purple arrows are sweeping through the entire region, no breaks. Okay, so the purple one gives you the limits as going from left to right. So 0 less than or equal to x less than or equal to y. Y goes from 0 to 1. Okay, we cannot change the function, we cannot change the region. All we can do is, instead of doing y first, do x first. Okay, so we have you should tell me what is wrong with this. There's something not at all correct about this. What is it?
You're doing y first instead of x first.
Okay, so what should be the correct way of writing it?
It should be on the outside from 0 to 1, and then the inside 0 to y.
Yep.
And then dx dy.
Dx dy, yes. Okay, those are the things you need to pay attention to, right? All the variable limits should be inside, okay, and should be done first. All the numbers should be done outside and done last. Okay, those are the etiquettes that, you know, if you do things like I just wrote earlier, then that shows that you don't know what you're talking about. Okay, so these are the basic concepts that you should get right. Okay, now it's the integration part, so the inner one. Let's hope that this is not too bad. So e to the power of x over y dx. Okay, remember that in your calc 1, if you had e to the power of kx dx, it used to be 1 over k e to the power of kx. Okay, plus c, but no, that's the whole point, right? If you had a constant here, you divide that constant there. It's kind of a u substitution, but we have done this so many times. So in this case, k is 1 over y. Okay, because you're doing with respect to x, y is a constant, so it's 1 over k, so it's going to be 1 over y, which is y. Okay, so it's going to be the integral from 0 to y of 1 over k, which is y e to the power of x over y. I did this from 0 to y. Okay, so I just plug in k equal to 1 over y there, and then you are plugging in for x here, not for y. Okay, so this gives you y times e to the power of y over y, which is 1, minus y times e to the power of 0, which is 1. Okay. I don't want to make it all cluttered here, so let's e to the power of x over y. So that's a lower limit. Ye minus y. And then the outer integral from 0 to 1. Okay. We tried to squish it in here. Sorry for, so 0 to 1, e minus 1 times y. Okay, y is a common factor, so it becomes e minus 1 times y dy, which is e minus 1 times y square over 2, okay, which is e minus 1 over 2. Okay. It's amazing how these problems get so easy if you are doing in the right region and doing the right change of the order of integration and so on. Okay, becomes so easy and elegant. Again, these are very sensitive problems. If you change something here, this gets out of control. Okay, so these are waiting to be kind of going wrong or almost impossible to be done if you change some numbers up there. Okay. All right, so do the homework problems in this type of problems, please. Okay, those are all kind of nice examples. Do them, and if you have any questions on those, ask me during office hours. Okay, and the quiz this week will definitely have one of these types. So I want you to be familiar with drawing simple regions and reversing the order. Okay.